Hi, everyone. We're going to talk a little bit about power calculations, and in particular, we're going to engage with a little bit of R programming to illustrate the power calculations we just talked about in lecture 20. So, as a reminder, in this example, we are considering comparing remdesivir to standard of care using a single arm trial to identify if remdesivir improves the probability that a patient will experience clinical improvement um, as a patient with severe COVID. So again, for more information on that, please see the Lecture 20 video. But this is an example we've been repeatedly engaging with in this class. So recall that we are imagining we know that the response probability, or the probability of experiencing improvement for patients with severe COVID on standard of care, is 0.66. And we are trying to see if remdesivir will um, improve that, will increase that probability, that response probability from 0.66 to something larger. And originally we engaged with a clinical trial where people had run this. Now we are imagining that we want to design a clinical trial, a one-arm clinical trial, where we only enroll remdesivir patients who we give remdesivir to and compare their response rate to that historical rate of 0.66. And we're trying to identify something like how many patients we should include, or maybe to start, we're just trying to consider a couple of different candidate number of patients to include and look at the power under different assumed alternative values, different true efficacies of remdesivir. So again, how do we think about calculating this power? And we're going to do it a little bit more painstakingly here than maybe one would do if you identify a library that will do a power calculation for you. So the first thing I want to do is think about our null hypothesis. So our null hypothesis says that the response probability on remdesivir is the same as standard of care, as 0.66. So in this case, I want to generate a sampling distribution for the proportion of patients who we might see respond to remdesivir in this imagined world where the response probability is 0.66 out of 100 patients we enroll. So again, as usual, the first thing we're going to do is set a seed so that we can replicate this. The next thing we do is we're going to imagine running 1 million trials. In each trial, we're going to enroll 100 patients. For each patient, we're going to flip a coin with a probability of 0.66 of them responding and identify the number that respond here, and then divide that number by 100, because there are 100 patients, to get the proportion of patients who respond. So if we run this line, we have this new object sampling dist null, and I can look at that, and what we see is it's a lot of numbers, right? It's just all these different proportions, one for each trial that we ran. So we can now look at a histogram of this, and I have this optional argument for xlim telling me what the x limits of my histogram are, and we'll see I want to use this, oops, didn't want to run that. I want to use this in the future to compare this null sampling distribution to the alternative sampling distribution we're going to engage with. So here we see, on average, about 66% of our patients respond, and we see, in general, somewhere between 50% of our patients and 80% of our patients responding in this null scenario where the response rate, or response probability on remdesivir is 0.66. So again, using this, we can get our critical value for a test of this null hypothesis. Here we're going to use a one-sided test, and we're going to engage with a level of 0.05. So what we want is we want to find the cutoff such that only 5% of the histogram falls to the right of that cutoff. And we do this with the quantile command, identifying the 95th quantile. So I'm going to do that. I'm going to call that value critical.val. And now I can evaluate critical.val, and I can see, that is 0.74. So if we had drawn a line, a vertical line at 0.74, what we would have is only 5% of the area of this histogram would be to the right of 0.74. And in fact, I'm going to add that to my histogram. The way you add a vertical line to a histogram is you say AB line, and then the input's name is going to be V, it turns out, and you can say equals, And then the value here, maybe I'll make it 0.74, and I want to make it red. So I say col equals open quotes red, close quotes. And now if I run this, there we go. That's our vertical line indicating our critical value, and only 5% of the area of this histogram should fall to the right of that value. Great. So again, this is a sampling distribution for the proportion of people who respond to treatment under the null hypothesis. Our question is now not what happens when the null hypothesis is true, but what happens when remdesivir is actually effective, when the alternative hypothesis is true. So again, we have to ask ourselves, well, what value of the alternative hypothesis do we want to understand the power under? What value do we either think is true, or as Brandon was noting, what is the minimum value we would be interested in being able to detect? So let's imagine we either believe that the response probability on remdesivir is 0.8, or maybe we think that anything below 0.8 is not really clinically important or clinically worth detecting, which again, in this scenario, may be totally wrong. We might be interested in detecting something less than that. But again, for the sake of doing this evaluation, let's imagine we wanted to identify the power under an alternative scenario where, in truth, patients on remdesivir had a 0.8 probability of responding, or an 80% chance of responding. So what do we want to do? Rather than looking at the sampling distribution of the proportion of patients who respond under this null value, 0.66, we want to instead look at the sampling distribution for the proportion of patients who would respond under that alternative value where each probability is 0.8. So we do that. Now we run this rbinom command again, except now where we had 0.66, we now have 0.8. So we're essentially flipping a coin 100 times, each time with a 0.8 probability of heads, and measuring first the number of heads, then the proportion of heads, and we're running that experiment 1,000,000 times. So again, we can do that. And when we do that, we can now look at our histogram associated with that. And we see this histogram is shifted to the right. I have the same x-axis here, right? So again, on average, generally we see roughly 80% of patients will respond to treatment in this imagined world, but it could be anywhere between something like 70% and 90%. And just as a reminder, before we did all this work to identify our critical value of 0.74, and there we said our trial is deemed a success if more than 74% of patients respond. Well, in this imagined world, how often will we have more than 74% of patients responding? So there are various ways we could go about doing this. One thing we could do is we could actually add a vertical line there. And I'm going to do that now. So this is a vertical line at 0.74. Oops. Here we go. And we see again, for all of these cases, we would be able to declare our trial a success and identify a significant difference between the proportion of patients we observe and that value, that null hypothesized value of 0.66. So we want to quantify what proportion of the histogram this is. And so one way we can do that is using the prop table and table command. So maybe we want to unpack this statement. This inside thing, we are taking this, this object sampling dist alt 80, which again is just a vector of numbers. And we are comparing each of those to 0.74, and we are trying to identify for each one, is it greater than 0.74 or is it less than 0.74? So running this line will result in this sequence of trues and falses. For each trial, it says, did we reject the null hypothesis in this simulation, or did we not? So we get a bunch of trues and falses, and then we want to identify what proportion of those are true and what proportion of those are false. And so when we run this whole line, we end up seeing the proportion that are true and the proportion that are false. And here we see 91% are true, 91% are greater than this, and 8% or close to 9% or less than this. And I realize greater than or equal to versus greater than, in this case, makes a big difference, right? If I use greater than or equal to, accidentally I get about 94% power, whereas if I just use greater than, I get about 91%. That's not a big deal, but I realized I should be using greater than, which will give a slightly different result than what we got in class. Anyhow, again, taking a step back, what does this mean? This means that under this imagined alternative, where the response probability on remdesivir was 0.8, roughly in 91% of trials, we will reject the null hypothesis correctly because remdesivir here is effective. So our power in this case would be 0.91 or 91%. And we would say that, again, our power to reject the null hypothesis when the response probability on remdesivir is truly 0.8 and we enroll 100 patients and use a one-sided test at level 0.05 is, the power in this case is 91%. We have to specify all of those pieces because they're all important in identifying what our power is. Great. So again, this was one power calculation for one sample size, right? For one value of the alternative or effectiveness that we believe for remdesivir. We could now try to do the same thing. We could think about changing this 0.8 to a different value and rerunning this and calculating power. Or we could think about changing our sample size and rerunning this whole procedure and calculating our power. So let's imagine, again, we really believe the response probability on remdesivir is 0.8, but somehow 90% power is not good enough, perhaps. Perhaps we want 99% power or something like that. We could imagine trying the same thing, only increasing the number of people on our study to 200. Again, generally, in this case, our power is high enough, so we wouldn't really worry about increasing the number of people on our study, but in other cases, we might think about varying that. All right, so now we're going to recalculate power, now with 200 people on our study rather than 100. Well, the first thing, when we have 200 people on our study, our critical value will change, right? So what do I mean by that? Well, let's re-engage with all pieces of this process. The first thing we did was under the null hypothesis, when the response probability on remdesivir was 0.66, we wanted to see what likely or reasonable values for the proportion of responders on our study was. So again, by running these lines, as an aside, really strongly parallel these lines, only I've changed 100 to 200. And I've changed the names of some variables so I don't overwrite things. So if I run these lines, now this is a sampling distribution for the proportion of patients who respond to remdesivir when the null hypothesis is actually true, when in fact each patient has a 66% probability or chance of responding, right? And so again, we use this to identify our critical values, our critical value in this case for a one-sided test, and we see now our critical value is 71.5%, where before our critical value was 74%. And what has happened here is as we have increased the number of people in our study, the sampling distribution for the proportion of responders under the null has gotten less wide. It has shrunk. So here's our sampling distribution with 200 people. If we go way up here, we can look at our sampling distribution with 100 people. Keep an eye on that plot. What happens, right? With 100 people, the sampling distribution is wider, right? With 200 people, where are we? Right here, the sampling distribution is narrower, which results in that 95th quantile being further in, right? And our critical value then being smaller, right? So before we needed to see much more than 66% of people responding to declare significance. We needed to see 75% essentially responding to declare significance. Now, or greater than 74%, now we only need to see greater than 71.5%. Excellent. So we have calculated our critical value. Remember, that's the first step in engaging with our power. So for this case with 200 people, we thought about right here what the sampling distribution looks like if the null is true. Now let's think about what the sampling distribution looks like if the alternative is true. So, okay, so again, in this case, what do? Well, we think about trials that enroll 200 patients, but now each patient, rather than having a 66% probability of responding, actually has an 80% probability of responding, right? And we want to generate a sampling distribution under that assumption. And again, just remember, 80% is some number that maybe I felt like was meaningful, or was my belief on maybe what the effects, what the response probability of patients on remdesivir was, or maybe was my thought as to what the minimally clinically significant response probability on remdesivir might be. And so that's the value that I'm using to size my trial. In practice, if a doctor were engaging with this, they would probably use a very different value than 0.8. But 0.8 is a value that we can modify based on either our beliefs or our thoughts on what size of an effect we would like to be able to detect. So I run I run this line. This now has run 1 million different trials, each enrolling 200 people, where each person has an 80% probability of responding or improving. I can look at a histogram for this sampling distribution. And again, what I'm going to do, is I am going to compare this histogram to the cutoff that I identified above, right? So what cutoff did I identify above? I said, okay, in this example where I'm enrolling 200 patients and my null hypothesized response probability is 0.66, right? I will call any trial where more than 71.5% of people respond significant. So I go down here and I say, okay, in what proportion of these trials under the alternative, am I going to observe more than 71.5% of people responding? It's going to be basically all of them, right? And I can use that similar prop table functionality to do that. And here I see that in roughly 99.7 of them, in almost every single one, right, I have cleared that critical proportion of 71.5%. So again, big picture, we have two sampling distributions we care about, one under the null that gives us our critical values that we need to exceed to reject the null hypothesis, and then one under the alternative that we use to understand how often we exceed that critical value or that threshold of significance, right? And what did I do? I thought about modifying the number of patients, right? We talked about how we could potentially just modify the effect size, in this case, the probability of responding under remdesivir. And this is just a one-arm trial, and more complicated trials, two-arm trials, trials with continuous outcomes, there are sort of different quantities we need to take into account when we're thinking about power and engaging with calculated power. So I did this kind of by hand using simulation. And in my mind, that's often the cleanest way to go about this. Classically, people couldn't do these things with simulation, so they did like analytical calculations. And those calculations are actually, people have written packages that engage with those calculations for us. One standard package is called PWR, and this has power functions to calculate power under a variety of scenarios. Often in those scenarios, they ask you about an effect size. And one thing to note in this package is that they quantify effect size in sort of slightly strange ways that make sense with regard to classical statistics, but aren't necessarily the way we would clinically or scientifically most naturally quantify effect size. And so that's one of the reasons that I'm not directly engaging with that package. Anyhow, hopefully that is helpful. Thank you. And best of luck.